First off, I'm experiencing a different level of what you're experiencing in terms of, did we already cover this? So, Calc 3 and linear sort of overlap for a couple weeks, and then we're going to diverge. Yes? One is going to take the road less traveled. But for the moment, we did dot product there, we just did dot product in here. Let's do this. Let me get back into where I left off. If there's no questions on homework, I'm just going to jump right back in. Finish up this chapter 1. Okay, there we go. So, what we're about to get into, a huge deal with linear is how to solve the equation AX equals B. Matrix times vector equals vector. And part of what we do to investigate the possible solutions to that is to talk about what matrices are. We're going to learn there's some kind of transformations. They take an input and they shift it a bit. That's one way to look at what matrices do. We're going to look deeper into the parts of that equation. We're going to look into the parts of a matrix. So we're just going to analyze the hell out of the components of AX equals B. Yes? We're going to talk about how to possibly know ahead of time if there's going to be one answer or infinitely many. We're going to talk about if there are infinitely many, do they exist in some defined way? Yes? So if I try to solve x plus y equals 7, 2x plus 2y equals 14, right? How many answers are there? X plus y equals 7, 2x plus 2y equals 14. Okay, let's look at this. X plus y equals 7. How many answers are there to that by itself? Correct? Somebody give me one answer to that. Give me one answer to that. Do it in. 1, 6. Ooh. 4, 3. Ooh. 77, negative 70. Yes? Anything that adds to be 7 is an answer. So there's an infinite number of answers to this equation, which is one reason why that equation sucks. Which is why if somebody gives me more information, I'm hoping it helps me narrow it down. Yes? And this is all stuff you've done before, but everything we do in this class is a little bit built on stuff you've done before, but 2x plus 2y equals 14. So I'm claiming I gave you more information, did I? Yes?
I'm sorry, what number is that?
Kind of in 1, 3. So I'm going to bounce between 1, 4 and 1, 3. And I think I explained last time, he references 1, 4 algorithms or ways of doing things in 1, 3. Yeah. What happens now? How many answers are there now? Infinite. Now, why? Because I gave you the same information twice, so I didn't really help you determine which answer was the answer. There's an infinite number of answers. Are they anything they want to be? No. Is 5, 11? 5, 11. Is that an answer? No. So there must be some way to describe the answers. How do you describe the infinite answers? Where do they live? Yes, they live on the line. What line? Yes. Okay, so this would be an infinite number of solutions, but the solutions are every point on this line. Some of you guys who've done the homework, you've already had problems where I said, describe the space of this, and you had to say if there's only one linearly independent column, it's a line. That's exactly what's happening here. How many linearly independent equations are there? 1. So the answer is line a line. Yes? 2. If I had two vectors describe a plane. So if I had 3 equations and 2 of them were independent, then all the answers, the infinitely many answers, would live on a plane. Yes? Maybe. Okay, so let's go back. Okay, so I try to give a little, so we're going to head in the direction of, and I've already put this up here before, we talked about it a little bit, but But thankfully, we're gonna take a turn into some more practical tools we can use. Yes, because as a student in here, I'm almost certain you're like, please, dear God, can we talk about concrete shit for a minute? That'd be great. Okay. One thing I want to describe. Let's go back. So we're not talking about this yet. We're gonna focus on the matrix part of it. So like I said, we're gonna focus on parts and talk about properties of those parts. We're gonna focus a lot on this. So if A was this here, so we're just gonna look at that matrix by itself. Can anyone see? I can't remember if I gave this last time, but just this would be a nice overlap. Did I give this one last time?
Yeah.
Okay. Couldn't remember exactly where I left off. I can't remember if I said this. I'm pretty sure I did. Do you guys see that row 3 or column 3? Sorry. Column 3 is how related to column 1 and column 2. Column 1 plus column 2. Yes. So how many independent column vectors are there? Huh? How many? 2. Yes, there's 2 independent column vectors. So this collection of vectors, what type of region do they describe? A plane. Because there's 2 independent column vectors, they can construct a plane. Can we stop for a minute? Any 2 vectors describe a plane. If I move them around, they're still describing the plane. Yes? If I had 1 vector, that can only move on a line. The line is in 3 dimensions, but it's just a line, poor little dude. Yes? And if I had all 3 were linearly independent, what do they construct together? R cubed. Okay. Which in general we just call a space. In fact, since I just said that, let's talk about this term, column space. And we kind of use this for a specific vector, for a specific matrix, the column space of A. So, in this problem, the column space of A can be created using what 2 vectors? 116, 240. Some multiple of this plus some multiple of this. If I take all linear combinations of those 2 vectors, I will create the plane that is the column space. So in this class, we're going to be discussing, this is going to be amazing. We have column space, so we also have row space. Then we're going to have some other spaces. And they kind of deal with the results of AX equals B, several of them. Okay. So here's another example real quick. I'm pretty sure I didn't put this one up here, but let's see. So what's up with this matrix? How many independent columns are there? This is pretty in your face, right? So you gotta be careful. Can I make the second column from the first?
Yes.
Yes. So the second column is not independent. Can I make the third column from the first? Yes. Just multiply by -1, yeah? So how many independent column vectors are there?
1, 2, 1.
No, it's 1. Yes? It's impossible to have no independent column vectors. I need you to understand that.
Shouldn't the third column vector, shouldn't the bottom one be -3?
Oh, it should be -3, yeah, sorry. Did I forget that before? No, I just forgot it now. Okay. All right, that was my point. Thank you. So if I could take -1 times the first column to get the third column, double the first column gets the second column. Is that cool that it's impossible to have none of the vectors given be independent? There has to be one. Or else you can't even talk about, can you combine some to make another one? Yes? Okay. Maybe. So what would the column space look like? There's 2 ways you can answer that question. what would the column space look like? Can you describe it? Would it be a plane? Would it be? Okay, so it's a line. So that's one way to answer this question. It would be a line. What's a more mathematical way to answer the question?
Constant multiple times 1
Say again?
constant multiple times 1 negative 1 3.
Yes, good. You could also say that this would be equal to any multiple times 1 negative 1 3. It'd be amazing if I could write. Because the other two columns don't give me anything new to construct other things with. I've already got that. So if you give me something in the direction of x, and then you give me something else in the direction of x, I can only make things on the x-axis. You give me no way to lift off of the x-axis in either direction. I'm stuck on the x-axis, right? My axis doesn't have to be one of the primary ones. Whatever you give me, if you give me just a multiple of it, I'm stuck on that line. Yes? Okay. So, let's bring in some definitions here, some ideas. The number of independent column vectors, the number of linearly independent column vectors is equal to the rank. We call it the rank of the matrix. So this last one we did would be rank 1. The one before it would be rank 2. Something else, give you a different example. How did you determine and I think I've used this word before, so I'm going to use it again, the basis vectors? Have you used the word basis before? Like in R squared, the basis vectors could be 1, 0, and 0, 1. Those two together make every other vector in that space, yeah, in R squared with me. So my column vectors are built from those two. Those two are the basis vectors. Okay, that word actually makes sense. Sometimes math people name things correctly. There's 2 of them, so I would say that that matrix has rank 2. How did you determine these? Where did they come from? Why did we pick those? They were the first 2 we saw that were linearly independent, yes? And then the last one was dependent on those 2. Technically, couldn't I use the first one and the third one? Because couldn't you argue, if any 2 make the third one, right? If the first 2 add to be the third one, isn't the third one minus the first one the second one? So if there's one dependent vector, column vector, it could be any of them, correct? So the method we use, just to make it kind of consistent, is we just take the first ones we see. Whatever the first independent one, that goes into C, column space. The next one goes into C. Okay, how are we doing so far? So this column space is a collection of all of the linearly independent column vectors as they come. What do those do? Those form the basis for the whole column space. So if I had, for example, let me finish this out before we do some examples. So the first R columns, linearly independent columns, form a basis for the column space. That's what I just said there.
So is 1 negative 1 3, is that independent?
It automatically is, if the way I'm looking at this and the way we've decided to do this, because there was a choice made. And what I just said was, if I know there's one independent one or two, I could call any of the other ones the dependent. So in this example that's on the board right now, that's the one where only one was independent, correct? Because the second one was double and the third one was negative times that. So pretty good. Couldn't you say the middle one, the second column, is independent? Because the first one is half of it, and the last one is negative half of it. You guys see what I'm saying? This is not a big point, but I need you to see the choice we make. We like to make algorithms, because what do we like to do with linear algebra? We like to program linear algebra into algorithms that can then attack things. So I want to make it standardized. We could have said but what we do is as we go through, we just pick them. Okay, the first one is linearly independent because there's nothing else there yet. It's automatically linearly independent. The next one, nope, it's a multiple. The next one, nope, it's a multiple. Is that okay?
So you could look at it left to right to left?
We could. Just like we could have called this the y-axis and this the x-axis. Yes, we could have done all our math that way. You guys agree? I could have called this the y-axis and this the x-axis. We would have done a damn thing to the math. It would have all looked very different, yes? But it would have all worked the same. Are you with me? At some point, we have to make a choice. So this is more of a choice of making it easy to make it a subroutine, for example. Right, just pick that one, and then check to see if any other ones are multiples of that or combinations with the other ones. I can tell a computer to do that very easily. Yes? Okay. So the first R columns, linearly independent columns form a basis for CA. The first column, the way that we've chosen to do this, will automatically be independent because nothing's come before it. Okay, I love you guys. Third point, and this one's kind of neat. Once I determine which column vectors are linearly independent, and they go into my CA, what combinations of the vectors in CA create the other vectors? So the examples we've done so far have been easy. I'm sorry. You're like, did you want us to see that? So a question we could ask the minute we created CA, especially if there's some vectors we left out, well, how do I create those other vectors, right? And then fourth, what we want to eventually be able to do is I want to be able to write, and we're going to be able to do this by the end of today. I want to, if given a matrix, I want to be able to write it as the column space, a column vector matrix. So this would have all of the basis vectors for the column space in it, times the associated row, set of row basis vectors, the row space. Let me stop for a minute. I'm going to do this with some simple examples where we can tease out the answer by observation. But I've said this before, very quickly, observation is not going to do anything for us. You got this disgusting giant matrix with who knows, and you're like, so I want a systematic way to determine, okay, which column vector should I pick? What is C then? And then what the shit is R? Yes? Okay, maybe. And just the last thing, I basically just said this, but the R is the row space, and it works the same way. Same idea as a column space. It doesn't work the same way, but it would be the rows that would create the basis for the row space. So it would be like the collection of the rows that are independent. Okay. Here's what's interesting. If there are two independent, in a 3x3 matrix, if there are two independent, well, actually any precise matrix, but if there are two independent column vectors, there's two independent row vectors, automatically. There's one independent column vector, there's one independent row vector, there's three independent, there's three. Let me stop for a minute. Okay. One little thing I want to show, just kind of a side note before we jump into some more stuff. If I put A, B, C here, and I want to make a 3x3 matrix, and I want that to be the only independent vector. Can somebody give me an option for the second column vector? I want that to be the only linearly independent column vector. Give me one thing that this next one can be. Don't say D, E, F. That doesn't. It's not. Yeah, multiply everything by 2. So maybe a little more out there. What could this one be?
Square A, B, C.
Say what?
Square A, B, and C.
No, not quite. Squaring it won't work. Squaring it won't work because remember these could represent equations, and I'm not allowed to just square an equation that doesn't maintain its equality. So I could put here, it doesn't really matter. I could put here negative 4a, negative 4b, negative 4c. Now, do you all agree that there's one independent column vector? And that's the only, this captures, well, I could have put D instead of 2 and F instead of 4, but this captures the idea of this is what almost all these matrices would look like if they have one independent column vector. What about the row vectors? Are they independent? The first one is. The first one has to be, correct? Because nothing's come yet. What about the second one? Can you guys see how the second one is a multiple of the first? Isn't it B over A times the first two? Do you guys see that? And what's the third one? C over A times the first two, yes? Does everybody see that? Yes?
Can you usually write it down?
Yes, I can. Do you see how this is A times 1, 2, negative 4? Is that cool? Do you see how this is B times 1, 2, negative 4? So isn't the second row vector just B over A times the first one? Because then the A's would cancel and the B would go in. And then the third one, the same idea. Yes? So this isn't like immediately obvious why, if there's one independent column, there's only one independent row. But this basically captures the idea of what would happen, right? And do you see that when I factor out the A, what do those numbers represent? 1, 2, negative 4. What do those numbers represent? The chosen multipliers we did. We multiplied the first by 1, the second one by 2, and the third one by negative 4. Yes? Okay. So it's always going to act like that. So that's why, if I have a matrix of one independent column vector, it will have one independent row vector. 2, 2, 3, 3. Okay. Tomorrow. Oh, get out of here. Oh, yeah, okay, good. So let's do, yeah. So let me formalize this. If A has R independent columns, it has R independent rows. Now, I want to take, I need to take a little divergence, and I think we did a little bit of this already. So I just want to make sure everybody's on board with this, a little side note. And then we're going to do an actual freaking concrete example of this. Can you guys take a minute? I'm pretty sure we talked about this the first day, but I want everybody on board with this. Can you guys take a minute and just multiply these two things here? How do you want to do this, Jeff? Let's do, let's just do this. Can you multiply those two? How big is this? 2 by 3, how big is this? Why is it that multiplication works?
Because they
Inner's good, and the outer tells me how big the answer's gonna be. Okay, so I know it's gonna be a 2 by 1. So if I do 1, 3, -1, I'm basically dotting it, and that is the standard way we do it. That's like that row picture we did last time, the row picture. And the column one was more combinations of the columns. But this is kind of like the standard way. If you ever did multiplication of matrices, we basically do dot products. So what do you guys get? Eight. And then, yeah, 4, 1, I get 8, 5. Yes. Now, if you did, let's see, yeah, let's do that. If I did the column picture, it would be twice this plus 1 of these minus 3 of these. And does that still give me 8, 5? Yes. So this is the row picture. And the row picture involves dot products. And this is the column picture, and the column picture involves combinations of the columns. Okay. Either way, it gives me 8, 5. All right, now, with that in mind, how to multiply these guys out. Let's look at this here. Sure. Lucky you, because they're like, we'll see it eventually. Okay, so this was pretty quick. This was pretty obvious. What's the rank of this? So what's rank do? It counts the number of linearly independent columns.
Rank 1.
Yes?
That's 1.
Yeah, it's rank 1. You guys see that? The second column is twice the first. The third column is 4 times the first, and the fourth column is 5 times the first. Okay, lose a negative. No, this time we got it. So this is a rank 1 matrix, which means the column space just has one vector in it, which means the column space has what shape? Linear. Okay, so column space is a line. The basis vector for the column space is what? 1, 2, -3, I like it. Now, watch this. This is kind of nifty. And this works, this is remarkably simple. I could have very easily made this horrific if I gave us 2 linearly independent, and then I made the third one 5 times the second one plus 4 times the first. I mean, I could do this spaghetti mess of shit. And then what we're about to do would not be anywhere near as easy. So I at least want to start with a very simple example of A equals CR. Then we'll talk about what to do when it gets way too complicated to do it this way. So let me write this down. We got our column space is 1, 2, -3. So I want to be able to write this like this. So I want this to equal my column space times a row space. And the funny thing with this problem, let me do this 2 different ways. Can somebody tell me, all right, this first column is what multiple of the column basis? 1. So if I do 1 times this, I actually get this, yes? The second column is twice that. This third column is 4 times that, and this column is 5 times that. And isn't that just the first row? if I looked at, now this is where I gotta be careful, because this only works for this one. If I row reduced this, do you guys see if I double the first row and subtract it from the second, I get zeros? And if I triple the first row and add it to the third row, I get zeros? Yes? So then what's the only vector left if I row reduce this? 1, 2, 4, 5. So that's going to be our general way to figure out R, is we have to use elimination. We have to row reduce the matrix. Thank the gods there's a method, because it's not always going to be as easy. I didn't do it that way. I just said 1 first column, double the second, you know. Okay. Can you guys take a moment and multiply this out? It looks easy as hell, yes? How big is the first one? Careful. 3 by 1, how big is this one?
4 by 4.
So the multiplication works, and how big will the answer be? 3 by 4. Do the first couple of answers and you'll see where it's going. Let me make sure you guys are really cool with how this is going to work. It gets a little trippy when both of these are really kind of skinny, but you do this row times this column. Yay! This row, so to get the first row, second column element, I take the first row, second column. So then to get the second row, first column, I take the second row times the first column, second row times the first column. So I'm just getting this, right? Of course I am, because A will equal C times R. So it seems to be kind of like a fundamental way to factor a given matrix. It sounds potentially useful. And remind me, what's the rank of this? Yeah, I like it. Okay, so let's try a slightly more complicated. So what I want you to do right now is to construct C. And what's pretty much always going to be one element in C? We said this earlier. Because by the time I get there, I haven't looked at anything else, so it doesn't have a chance to be a multiple of anybody or a combination. It's in! Woohoo! Can I put the next column vector in? Why not? It's a multiple of the first one. I love it. Now what about the next column vector? Is everybody cool with that? The second column is just 3 times the first one, or negative 3 times. What about the third column? What do you guys think? How many columns are there really by the time you get to the third column? No. Because the second column was just a multiple of the first, correct? You guys see what I mean? How many columns are there really when you get to the third column? 1. Because what's the second column? Negative 3 times the first column. Isn't that the same stupid thing? Yes? Just a multiple of it? I really want you guys with me. I'm going to show you, by the way. This is right after this, I'm going to show you how elimination answers a lot of these questions directly. But this one's not bad enough you can kind of tease this out. Does it make sense that 3, negative 15, negative 6 is effectively negative 152, just the longer version, it's just 3 times as long. It doesn't give me any more information about another direction, correct? So it's not new information. So I really just have one vector so far before I get to 4, negative 1, negative 3, yes? If I'm comparing two vectors, what's the only way that they're dependent? If one of them is a multiple of the other one. Is 4, negative 1, negative 3 a multiple of negative 1, 5, 2? No. Do you guys see that? And again, if you want to argue, no, I want to combine column 1 with column 2, well, if you just add those, don't you get negative 2 column 1? Any combination of column 1 and column 2 is going to be a multiple of column 1, correct? So if I have 1 column 1 minus 3 column 1s, don't I have negative 2 column 1s? So no matter what combination I make between the first and second columns, don't I just have the first column a multiple of it? Okay. By the way, this exact problem we'll do again, but in a more recipe-ish way. So anyway, thank the gods. So what's the next column, that vector I'll put in here? 4, negative 1, negative 3. So there's my column space. What's the rank of this matrix?
2.
Yes. How many vectors should be in my row space? 2, because they have to have the same rank. So what I want to think about, and this is going to be definitely more difficult than this was, if I have C, I have to consider, what do I multiply that by to end up with A? So here's one thing to realize right off the bat. Do you see how this already has parts of A in it? Yes? Okay. So do you see, don't I want the first column to be 1 times this? So that means that this is going to be 1, and do I want any of this column involved? I just want one of these. So the first piece of R is going to be 1, 0. Because what do I want that? I want one of the first columns and none of the second column, and that's going to make the first column an A. I could do the same thing with the last entry, because the second piece of C, 4, negative 1, negative 3, is the last column in A. So over here, same idea. What do I want to show up here? Do I want any of this? I want none of the first column, one of the second column to go in my third. That would make, I got the first column in A created, and I got the second column in A created. I love you guys. If you just stick with me a little bit, please. I can see your eyes. Some of you guys are like, if this class does not become more concrete. Okay. We're almost there. This is going to be really cool. I'm the only one that thinks that, I'm okay. How do I construct the middle column again? What do I need? How many of?
3.
I need 3 of the, well, how much? Say, negative 3 of the first column. Do I want to add any of the second?
No.
Do you see how we piece that together? And do you see how that could get remarkably difficult? Especially, what if A had been a 5 by 5 matrix with 3 linearly independent? Screw this. Yes, but that wasn't that hard. It was different than anything you've done before, but that was it can very quickly get disgusting. So let's do this. Let's row reduce this. We're going to do it by hand a couple times, and then I'll show you how to do it in the calculator. Does anyone have any clue how to row reduce a matrix? Every row, think of it as representing the half of an equation. So I'm allowed to multiply any row by whatever I want to. I can add 2 rows together. I can subtract 2 rows. I can switch 2 rows. Yes? And who knows my goal here? Where do I want to end up? Yes, sorry.
With like a 0 in the bottom left and pivot points, I think.
Oh, look at the pivot points going on. So my goal is to get this, if I can, become a 1. And so these ones on the diagonal, they're called pivots. So If you've never done this before, first off, I'm sorry. You really should have. If you haven't done it, not your fault. It should have happened. My goal is to get 1, 0, 0 in the first column, correct? So let's focus on that. I am allowed to multiply any row by whatever I want to except 0, and I can add or subtract any 2 rows together. Do you see how there's a beautiful -1 as a pivot because it's on the diagonal? That's awesome. The really weird thing is if you were creating a computer program, it would use 5. The highest pivot number, the highest possible pivot number is the more safe one for computer programs to not run into any freakiness. We're humans though, last I checked. I don't know. As far as I can tell. I think it's human. If I add row 1 to row 2 right now, does anything good happen? Do I get any closer to my goal? No. But if I multiply row 1 by something, I immediately get much closer to my goal, especially if I focus on the first column, right? What can I multiply the first one by? Say again, sorry.
5.
It's 5. So if I multiply, and I'm going to show you all my shortcuts here because we're not going to do this a lot by hand, but I just put what it would be because I just need to multiply by 5 for a second. I don't need it to be eternally multiplied by 5, right? So what do I get if I add the new row 1 to row 2?
0, 0, 19.
Say what?
0, 0, 19.
0, 0, 19. I like it. And then I have -1, 3, 4, and I have 2. Well, I can kill that last one too. Don't put the 2 down there. Okay, so these did its job. Go away. You're done. Do something similar now with the last row. What do I multiply the first row by to do a similar thing with the last part of that first column?
2.
Yes, sorry.
2.
Yeah, 2, okay. Multiply by 2, multiply by 2, multiply by 2, add, that's a 0. 0, that's a 0, and that is a 5. You guys good? Oh, what happened? I'm sorry. So if you multiply everything in row 1 by 2, you get -2, 6, 8. And then I add those to the last row. So remember, this first row could represent -x plus 3y plus 4z. And the last row could represent 2x minus 6y minus 3z, yes? So if I double this and add, these are like terms. And that is why they were put where they were put. They must be like terms, yes. Okay. What can I do here? Now notice I'm never going to reach my goal. How can I tell already that if that's my goal, I got to give up on it? What's one of my pivots that's bad? At the end, I want all my pivots, all my diagonal numbers to be 1. Can I make that happen now? No, damn it, because I got a 0 on both those freaking stupid pivots. The first row has a 1 pivot, so I need another row to have the middle pivot, and they both have a 0 there. Damn it. Can't I divide both by 19 and 5? You guys see that? I can divide the second row by 19, the third row by 5, yes. Okay. And then if I multiply row 2 by -1 and add it to row 3, I end up with this. And then I do one more thing. So even though I can't fully get to my goal, what is one thing I can make show up that I really wanted in my goal? I'm going to get as close as I can. Yes?
Add 4 of row 2 to row 1, or subtract that.
I love it, because you're trying to get rid of that 4 in the corner there. That 4 in the corner. So if I kill it, I'll have a 0 like my goal 1. Yes? So maybe I'll get like 4th place or something. I'm not going to get, oh, I can't get there, damn it. It's not our fault. The thing was rigged from the beginning. Maybe by me. So if I multiply this row by -4, the only thing it's going to affect is this guy because everything else is a 0. Is that cool? So then I get -1, 3, 0, 0, 0, 1, 0, 0, 0. If I took out that bottom row of zeros, have we seen the matrix that results before? Maybe like earlier today. Have we seen that? Like right there? And we got this from observation. So if observation fails you, which it will, because there's going to be some that just all kinds of weird shit happens, you can always do elimination. Any 0 rows you take out, and whatever's left is my row space. Now notice something else. Where are my leading ones? Which columns have my leading ones? The first column and the third column. Look back at our, man, that's hard to say. Look back at our column space. Which columns from the original matrix did we put into our column space? The first and the third. Holy shit! So if you use elimination, kill a 0 row, what's left is your row space. Your leading ones are your column space from the original matrix. Does anyone understand? Do you understand? The problem I gave us was simple, because it was just multiples and shit, yes? So it was easy to do by observation. But if you use elimination, not only will the rows tell you what the row space is, the leading ones tell you, hey, go back and pick these columns, that's your freaking column space. Okay. And if you're struggling to find motivation to be excited about this, A equals CR is a huge part of this class. So I have to come up with a way to figure out what C is and what R is. And now we have a definitive way to always do that. Okay. Yes, sir?
What do you mean by leading ones?
Oh, sorry. In the first column, where's the first one?
-1.
I'm sorry, in the first row, where's the first one? I don't know what that. This is kind of floating here for some reason. The first one is in the first column, correct? In the second row, where's the first one? The leading one.
The
Third column. So wherever the leading ones are, when you're done with your elimination, those columns are your column space from the original matrix. Okay. Yes, sir?
I'm just still struggling to figure out how we went from the -1 on the bottom row to the 0. Or the +1 on the bottom row to the 0.
If I multiply this row by -1, and then add it to row 3, excuse me, this will be 0, 0, 0. Yeah. Yes, sir.
Why did you just cross up the negative?
I think that was a stray mark, or was it supposed to be there?
It was in
It was supposed to be there. Oh, I forgot to divide by a -1. Is that what I did? Oh yeah, so one more step I could do is I can divide by a -1. There we go. Divide the first row by a -1. And now that perfectly matches with this. Okay. So here's the thing. I need you guys to be really honest. I think looking at y'all when we're doing the elimination, you guys haven't really done that much. It is kind of important. I am going to make you do some by hand. Yes? And the idea literally is, if it's in a column, they're assumed to be like terms. So all my X terms, all my Y terms, all my Z terms. That's why I'm allowed to add 2 rows together, because they're like terms. If I had equations, can't I add multiples of equations together to try to solve a system of equations? So I can add multiples of rows together. Yes? And if I had, you guys help me out. Blah, blah, blah. Can somebody tell me what this equation would be? What's one possible equation this represents? So, if I got down to this, why is that good? Because what's the first one say? X equals, okay. So, if I can get an identity matrix here, then I can read off the answers. Now, I want you to realize, the matrix we just did not represent equations necessarily. It was just a little equation just living by itself until we came along and poked it. Yes? We analyzed this matrix. It doesn't represent equations. I said it could, but it doesn't. But it still can row reduce. I can row reduce, this is called an augmented matrix. When I add the solutions on, if I don't add the solutions on, I can still row reduce the damn thing. Okay. What do you think it would mean if we had done all this work and we did get 1, 0, 0, 0, 1, 0, 0, 0, 1? What would that mean about the original matrix?
It's the same matrix.
How many independent columns would it have? 3. What would the rank be? 3. What would the row space rank be? 3. I love it. Yes? Here's something trippy. Let me see. Real quick, should I show you? Sure. Did I bring my calculator? Yes. So if you don't have a calculator, I'm sorry, I didn't bring any with me, but just to show you here, you'll see a very neat button. It's above the x to the negative 1. The matrix button. Okay, so if you want to play along, I'll wait till you get all your calculators out. I've already got some matrices built in there. So does everybody see above your x to the negative 1, above your reciprocal button, is the matrix button. Right below the mysterious math button. Anybody, when you first got this calculator, did you hit the math button? I'm like, that's the first. I'm like, math. Okay, after the on button, math. Do math. All right. So if yours are all empty, you're fine. So if you select, so don't hit names. That's how you can tell the calculator. Oh, go pick A. I haven't made A yet, so go to edit, and then I can edit A. So if yours currently says 1 by 1 or whatever, let's make it 3 by 3, right? 3 by 3. And then we're just going to put these elements in. Yes? Negative 1. Go ahead. I won't talk out loud. Where'd it go? Okay. Oh, I forgot a negative. I love it. That's the worst thing. So always double check. Maybe even triple check. Because all it takes is one negative and the whole thing goes to shit. As somebody saved me from earlier, which I appreciate. So now, this calculator, by the way, the TI-8384, one of the main things it's directly built for is statistics. All the statistical functions are easy. It's not built for matrix stuff. So we kind of have to, if you put your matrix, you have to hit second quit to get out of your matrix. Right above your mode button, quit. Now go back to matrix. I want to do math to the matrix. I want to do, the full name of this is actually row reduced echelon form. RREF. And I want to do that to matrix A. So go back to your matrix, tell it you want A, and then that looks very familiar. Yes?
Welcome back.
Yes, ma'am.
During exams and quizzes, do you expect us to use our calculators for?
I will say, so on the first exam, I'm probably going to have one problem where I want you to do by hand.
Okay.
But we are going to have so many other things to worry about based off of what the results are here that I'm okay with eventually just doing it in the calculator. But we need to know what goes into doing this. We have a lot of other stuff we're going to do by hand, so I'm okay with letting go of this one. Just make sure you know how to row reduce because you are going to have to do that a few times. Yes? Yes?
I don't know what step it is, but it's when we went from.
Here we go. I'll do it again. Sorry, man. So go
No,
to.
it's the previous, not
Oh.
calculator. Where it's negative 1, 3, 4, and then 0, 0, 1 times negative 4.
Yes.
Why did also leave a 1 when you did that? Wouldn't it be negative 4 minus?
Oh. Do you see how I multiply this first row by 5?
Okay.
And then I erased it? I divided by 5. So why did I need there to be a negative 4 here so I can kill that 4?
Okay.
Once that 4 is dead, do I need this to be negative 4 still? So then I can just kind of effectively divide by negative 4.
Oh, okay. I
That's why I don't rewrite my matrix. I just put next to it what it would become because I don't need it to be that, except for that instant. Yes? Okay. So hopefully it seems like it's coming back to a few of you guys. If you really feel like you've never done this before, you're gonna want to, bless you,
Thank you.
gonna want to practice a little bit. I got a handout up in Canvas, like I said. It's got a fully worked out problem. It's crazy sauce. Okay. And if you're really upset because you have this technology that can do all this for us, well, too bad. You don't learn anything by pushing buttons. You learn it by doing it. But this does very quickly become busy work. I'm very aware of that. So I'm not going to make you reduce an 8x8 matrix. Right? I don't think so. Depends on how I feel. Yes?
During the exams when we're hand doing it, are we allowed to use our calculators to check the
Oh,
answer?
hell yeah. I can't stop that shit. If you don't check what it should be in your calculator, yeah, totally do that, please. Just be careful about garbage in, garbage out. You forget a negative,
It's all.
and you're like, am I wrong or is it wrong? Oh, shit. Okay. Couple little side notes about matrix multiplication. And I'm pretty sure I said this before, but just to be certain, is matrix multiplication commutative? What's up? Is it commutative? Can somebody come up with a very, very quick example that would show me it's not commutative? You don't even have to do any matrix multiplication.
You can't do it 2 by 2 and 4 by 2.
Okay, good. So like if A was 2 by 2 and B was 2 by 4, yes? I know what you said, but let me, that's doable, correct? And what would BA be then? Is BA doable? That's beautiful. I didn't do any matrix multiplication, but I can show somebody AB is doable. It doesn't even matter what the answer is, because BA is not doable. It's automatically not commutative. Now, if they were both 2 by 2, almost all the time, if you flip it, you're going to get a different answer. Okay, maybe. We're not used to that with multiplication of normal mathematical objects, but these are not normal mathematical objects. And our definition of multiplication is freaky, so, okay. What about associativity? What do you guys think about associativity? You think this is true? Yes, that one's true. That one holds. And again, you could prove that. Well, you could throw some stuff in there, but you could give yourself some dimensions to kind of feel this out. The proof would be difficult because how big could a matrix be? Infinite. So you can do a proof, you'd have to just represent all the elements and then it just gets unwieldy, let's just say. And finally, what do you hope happens here? Yeah. Now let me see. All right, I'm not going to do this. Here's the answer, yes. What if somebody wrote this? Nope. So every time, so in our future, we're going to have an equation like AX equals B, and we're going to multiply both sides by a matrix. So for example, this is going to be in our future, AX equals B, and maybe for some reason, I'm going to multiply both sides by C. So if I do this, is that okay? No. So matrix multiplication not being commutative means that not only the fact that I'm multiplying by C, but the fact that I'm multiplying by C on the right side, or in this case, the left side. Sorry. So if I multiply by C on the left side here, I better multiply by C on the left side there. So now, doing the same operation to both sides drills down more than normal. Not just a multiply, but you're doing left multiplication. That you're allowed to do the same thing to both sides. You can't do one side left and one side right. That's not guaranteed to be anything true. Okay, how are we doing so far? So this is just one little thing we're going to run into later because of how matrices work. Well, basically because how we define matrix multiplication. Okay. Yeah, a lake. So what if all columns of A are independent? Linearly independent. So for example, if I had a 3 by 3, so everything in this 3 by 3, column 1, column 2, column 3, if they're all linearly independent, what would R be? No. Real quick, if all three of these are linearly independent, what's the rank of the column? Column has rank 3. What must the rank of the row space be then? 3. Sorry. And remember, so here, let me give us an example. Let's see if I can do this. 1, 2, 3, 4, 5, 7. -3, 1, 2. Okay. More than likely, that's linearly independent. It's really difficult to create a truly, I'd have to double check, but let's just pretend like that is. If that is linearly independent, when I row reduce it, what will I get? Will I get any row of zeros? I will get the identity matrix. Now help me out. How did we figure R? We row reduced, and whatever was left, if I had a row of zeros, I removed it, that was R. If I row reduce this, if I roof this, I will get 1 0 0 0 1 0 0 0 1. Is that cool? The whole reason you might get a row of zeros is because of dependence. We just said they are linearly independent. So what's my row space for this? The identity matrix. So what must the column space be then? And the funny thing is, I mean, what would the column space be? Isn't it just the collection of all the independent columns that we just say they're all independent? And doesn't it make sense that this being C and this being R, by definition, identity matrix times a matrix gives you what? That matrix. So of course this is freaking A. So if I have a situation where all my column vectors are independent, I have no work to do. If I can just see that, I'm done. R is the identity matrix. C is all the columns. Where are my leading ones in my R? In my row reduced? Where are my leading ones? First column, second column, third column. So which columns are independent from the original? All of them, all three of them. Yes? Okay. I like it. You would, Jeff. Okay. Okay. So I'm going to get a little bit into 2-1. We basically, 1-4 is all about multiply matrices, and then it talks a little bit about C and R. 1-3 we finished at the very beginning of class. So we've just finished chapter 1. Chapter 1 has some stuff you can sink your teeth into, but it's a lot of kind of theory stuff. So some of the homework, I like that. Please, dear God, let me know if you have trouble with the homework, right? You're never alone on this homework stuff. There are people in the center that can help you out. There's me, but if you're tired of listening to me, you got other people. Okay. You even got this dude, the guy who wrote the book. You can go watch his lectures. So we're going to talk a little bit about chapter 2, and then we're going to head out. Maybe, let's do one more example. What do you guys want to do one more example or get into 2?
Get into 2.
Okay. One more example? Let's see. I can make this a democracy for a second. Okay. The guy who said get into 2 said it louder. No, I'm joking. So, one more example. Let's say this is my... Okay. That's my matrix. Can you guys, is it okay to try to do this by observation very quickly? Do you see how the elimination will be really quick? I mean, there's only 2 rows, yes? Well, let's see. Let's try to tease out a little bit from observation first. You with me? So if I was trying to construct my column space, so the collection of all the linearly independent column vectors, what always goes in there? First one. Do I use the second one?
No.
No. What about the third one? Is it independent from these 2, considering this isn't really here, yes? Because it's just the same vector twice? All I need to know is this is not a multiple of this, correct? So do I use 3, 1?
Yes.
Yes. What about the last one?
Yes.
Now be careful. There's a little twist. I'm still okay with trying to have us do this by observation. What is the first plus the third? Okay. So you can see how even that's not terrible, but it's really easy to miss. So let's verify what we just did. Is everybody cool? That's my column space, yes? Because the last column is the addition of these 2 columns. Can you guys go ahead and try to row reduce this? And it's really nice because I put a 1 for you already up there in the first pivot. I don't know if any of you have ever watched Friends, but every time I say pivot, I think about that one episode. But pivot. So again, the row reduce. You know you're trying to, now this is a little weird because there's no identity matrix for a 2x4. But what you're trying to do is you're trying to get as many zeros as you can. So you can certainly get a 0 here, yes? So what are you guys doing? What would you do to the first column? So you can add it to kill this dude. Multiply by 2. I like it. And now you see we get a kind of a 2 for here. So the first stays the same. And then 2 minus 2 is 0, 4 minus 4 is 0, 6 minus 1 is 5, 8 minus 1 is 7. Become a 3. Did I do this wrong? 6 plus 1 is 7. Yeah, that's better. Okay. I'm not good with numbers. So that's better because now what can I do with that last row? I got 2 zeros out of that. That kicks so much ass. I want zeros. When I can't reach my goal, I change 2, make as many zeros as I can. What can I do with that last row? Divide by 7 because the next best number besides 0 is 1. And then is there one more 0 I can eke out of this thing? Right? We become little 0 demons. We're like, just make everything, we're nihilists. Everything is 0. So what would I multiply that second row by? -3. Yes.
How do you choose between changing the 3 or the 4 into 0?
Oh, okay. I want, how do I say this? I want leading ones. So I want, do you see how there's a leading one with a 0?
Mm-hmm.
Isn't this my leading one in this row? So I want the one above this to be 0. Okay. That's it. So whatever our leading ones are going to be, I want the other things there to be 0, if I can. Okay. So if I multiply this by -3, these are still 0, of course. And what do I get from that?
1, 2, 0, 1, 0, 0, 1, 1.
Now, leading ones are in column 1 and 3, and the columns we picked for our column space were 1 and 3. So our column space for this problem, we first did it by observation. Observation fails very quickly when there's really weird multiples going on. This will never fail. Leading ones tell me which columns are my column space. How do I put together my row space? Well, it's put together for me already. What's my row space? 1, 2, 0, 1, 0, 0, 1, 1. What was my rank for my column? 2 in my row, and that matches what the rank is for my A, which was 2. Well, the rank of A is because there's 2 column vectors, but okay. You guys get that? So that is a kind of a natural way to factor any given matrix. Okay. Since we define matrix multiplication, it's very natural to think, okay, there must be a way to undo multiplication. Let me see. Oh, look at that. I got something. Yeah, okay. Oh, by the way, what does this tell you here? What does this piece tell me right there? Yeah, if I multiply the first column by 2, I'll get the second column. And what does this tell me? If I take the first column, if I take the, what am I trying to say here? If I take the last 2 columns, you see, if I double the second column, and this one says if I add the first column, not the second column.
Can you do this to C? Like you add the first column.
Oh, here I am. Thank you. I was looking like this was together. If I take the first column and the second column, it would create what you go here. Thank you. Let me write this down for myself. There we go. This is what I thought I was looking at. Okay. So if I take the first column, add it to the second column, I get what goes into the fourth column in my original matrix. Cool. We didn't have to do that by observation, but when you're done with the row reducing, you can actually go back and see does it make sense. Okay. Okay, so stepping into 2-1 just a little bit, where we're going to start looking at this thing. So it's matrix times vector equals vector. So one way to look at this is whatever the matrix A is, it applies transformations to X, which turns it into vector B. So if I feed it a vector X, matrix A will do several things to it and turn it into a different vector. So geometrically, it could be like that picture I have where it kind of tilts something. You can feed it a space and it could do stuff to it. You can have higher level equations, but we're just going to focus on matrix times vector equals vector. So here's one example of this in action. So this is, where's matrix A in this?
1, 2, 2.
Yeah, this is A, and what's this? Be very careful, no?
B.
B. So, let me do this for us. Here is this one literally wrote out. Sure, we'll do that, Jeff. No, Jeff. I always want to make it a fraction. If I multiply 1, 2, 2, 3 by xy, what do I get? I get x plus 2y equals 3, yes? If I multiply these, don't I get x plus 2y equals 3? And isn't that what this says? Okay. So you got this augmented matrix version, and then you have this one, which is more literally exactly what this says, yes? And then if you multiply it out, you can get back to the linear, the basic algebra equations. Okay. So let me ask you this. The only way this could have one solution is if this vector is in the column space of this. The only way this could have at least one solution is if this vector is in the column space. And somebody remind me, what's the column space mean? Yes, and what does it create then? What's the column space? So the basis vectors for the column space are the independent column vectors, yes? If I take all combinations of them, that creates the column space. So another way to look at the column space of a matrix is it's all the vectors that they could together make. If I take all the linear combinations of the vectors, that gives me the column space. Yes? Yes?
So if it's just like one where we independent.
Then it's just a line, exactly. Then I can just get multiples of that. So, for example, we'll see in a minute. What do you guys think, just looking at this? Do you think 1, 2, and 2, 3 are linearly independent? There's only 2 vectors, so who knows right off the bat that they are? Can you guys see that they are? Since there's only 2 vectors, the only way they can be dependent is if one is a multiple. Yeah, so those are independent. Yes? So is 3, 5 in the column space of this matrix? If they are linearly independent, do they cover the entire R squared? Yes. So can I make 3, 5 out of them? Yes. Okay. So that is going to have an answer. Okay, I love it. I love it. So we're sort of merging some of the stuff we talked about before now. So to make one that has an issue, let's see if we can identify the issue. So first issue is what? If you just look at the matrix part, not the B part, but the matrix part, what's the immediate issue there? Yeah, what's the rank? 1. So it's missing something. It's not missing something, but it's missing information because one of them is just a multiple element. More importantly, though, it could still be an answer. That could still work if that 3, 7 was in its column space. Is it? 3, 7 is not something that can make. Yes? Do you guys see that? Yeah, like it. So that has no solution because I cannot create the vector 3, 7 from the vector 1, 2 because that's all I have to work with. So what if I had this instead, of course? So no answer. This is not in column space. I might as well just use all the space, Jeff. So of course, all I can do then, I could do this. 1, 2, 2, 4, 3, 6. Does that have at least one answer?
Yes.
Because 3, 6 is in the column space of that. And we actually know how many answers there are. Infinitely many. So I just showed you in succession one solution, because these are independent, and this is in the column space. No solution, these are not independent, this is not in the column space. Infinitely many solutions, because these are not independent. In fact, can you tell me where the solutions sit?
On that line.
X plus 2y equals 3. That has all the solutions, yes. Okay. Let me think. Oh, that's fine. Sorry. Oh, I do not mind if you remind me that we stopped at 520 because pretty sure we do stop at 520. I can't remember. Yes. So this is exactly the example we did earlier, where the first equation is x plus 2y is 3, and the second equation is double that. So, yeah, that matrix 1, 3, 2, 4 has one independent column. So those 2 vectors are not really independent. So there's an issue with that, but it lucked out because 3, 6 is actually multiple of that vector. That's why it still has that answer. One line at 7. Really should have. Yeah, the 7 is no way to make that issue. Yeah. 1, 1, 1, 2.